Everyone, we're moving into chapter 23 here, which is electric potential. We're not in electrostatics anymore. Charges will feel forces, they will move, and we want to analyze the energies that they possibly have in different situations. So we've played with the Van de Graaff generator a lot. You can see the field lines around that girl's head, just like a point charge. The field lines are pointing away or towards. Before we go into anything with this idea of what electric potential is, we need to go back to a quick recap of work and energy. If you go back to Unit 6, we talked a lot of different work demonstrations, and we calculated the work done, and we talked about work being positive, negative, or zero. So I'm going to do a couple scenarios for you. In each scenario, you need to tell me whether the work is going to be positive, whether the work will be negative, or if there is no work done, and we want to see what happens to the object's potential energy as a result. And mainly we want to focus on the work done by a field. So not the work done by a person, because you'll see me doing some things here. We want to look at what the field is. In this case, we're going to do a gravitational field and then relate that to electric fields. You can see that I'm standing in my room, and the gravitational field is pointing down in all directions. No matter where I am in the room, the gravitational field you could see as nice uniform lines pointing straight down like we have in the picture here. What I'm going to do is move things in this gravitational field. So I have your textbook, and I lift your textbook up over my head. If you want to think about what's going on here, work was done. If you want to think of the work I did, I applied a force up, the book had a displacement up, so I did positive work. But I said what we want to focus on this time is the work done by the gravitational field. So the work done by the field is negative work. Because the gravitational force is down, the object moved against the field, so we had a negative work done by the field and an increase in the potential energy of the book. How do I know it has more potential energy? Because I know that it wants to fall down to lower states of energy. Scenario number 2. I'm going to take that same book and lower it in the gravitational field. So if we look at the work done in this scenario, you've got my fingers pushing up and the book is moving down. So now I am doing negative work, or the book is doing work on me. The gravitational field, though, is pushing down and the book moved down as well. So now the gravitational field is doing positive work. And if we analyze the change of potential energy, we have lost potential energy. So with positive work done by the field here, we have a decrease in potential energy for the book. Scenario 3 is moving the book left and right in the field. So again, the gravitational force is straight down, but now the displacement of the book is left and right. And with the displacement being left and right, they are at 90 degrees to each other. And since work is a dot product, we're getting no work done by myself or no work done by the gravitational field, which means that my potential energy has remained constant. So it hasn't changed at all, because if you think about it, I'm still at the same height everywhere I move in that gravitational field. If we want to look at the work done by the gravitational field here, what we need to do is calculate the work done by conservative forces. And what we can remember is that work done by conservative forces is negative du over dr. So it's the change in potential energy over the change in position. And since it's a conservative force, we put that minus sign in there. Why do we put the minus sign in there? Because conservative forces want to decrease our potential energy as quickly as possible. So if we had our gravitational field pointing straight down, and let's say we move a mass in this gravitational field from location A to location B. And remember, with conservative force, it's path independent. It doesn't matter how I get the object from path A to path B, we can analyze the energy from start to finish. So if I want to solve for the change in energy, du equals negative force dot dr. And I'm going to integrate both sides from no energy to having all the change in energy. So du is just going to become my change in potential energy. In this case, the force in a gravitational field is mg, which is down. So it's technically negative mg. And all we're going to have to integrate here is just dr. Where am I going to integrate dr from? From A to be. So when we integrate dr is just going to give us our change in position, and we'll just call that the height. The height of the object going from its start point to its end point. So you can see that we can get mgh again from solving for a change in energy for the work done by a gravitational field. So in all three examples there, we could see work done by myself and we could see work done by the gravitational field. What I want to focus on is the work done by the field and how the energy changed. So we have a new rule for nature here. The new rule says that if the field does the work, so if the field does positive work, then potential energy is going to decrease for our object in that field. If work is done against the field, so that means if I lifted the book in a gravitational field, then that was negative work done. So when negative work is done against the field, an object's potential energy increases. And if there's no work done by the field, meaning you move left and right and the field's straight down, then the potential energy of the object will not change. So let's look at two more scenarios and see if this rule of nature applies. So in example 4 here, I dropped the book. So when the book is dropped, you can see that the gravitational force is down, and if we look at just the field is doing positive work. It's pushing the book down, the book is moving down, and since the field is doing positive work, go back to your rules and see that yes, the potential energy must decrease. And it did. The book went from a higher height to a lower height and increased its kinetic energy. So when you launch a book in the air, we can analyze kind of 3 locations. We can analyze it on its way up. So when it's on its way up, the field is doing negative work. Field's pushing down, book's moving up, and the potential energy is rising. And if we know conservation of energy, we know kinetic energy is decreasing. When we reach the top of the peak, at the top of the peak, we are at maximum potential energy. We have no kinetic energy, and the object will not want to keep that new potential energy again. Objects want to lose potential energy as quickly as possible. What we have then is the field doing positive work to bring the book back to me. When the field does positive work here, we see that potential energy decreases and kinetic energy goes up. So let's equate this to charges. We saw what happens to masses in gravity fields. Let's look at charges in electric fields. So I'm going to fire a charge towards another positive charge, and I want to kind of go through this checklist. So here's the scenario: firing a positive charge towards another positive charge. First question says, does the velocity of the fired charge increase or decrease? As this little charge tries to move towards the big charge, remember there's an electric field that points away in all directions. So just knowing how charges interact with electric fields, that positive charge is going to feel a force away. First thing on the list is that the velocity will decrease. So let's go to the next thing. If our velocity is decreasing, that means there must be a force acting on it. So we're good there. But is the force constant? Well, since we're moving closer and closer to a point charge, as we move closer and closer, our velocity is going to get less and less and less. As our velocity decreases, we know that the electric fields and the electric forces from charges fall off by 1 over r squared. So yes, a force is present, but the force is not constant. The force is changing by 1 over r squared. Let's look at the next one. Is there an electric field acting on this? Well, forces on charges come from fields, so yes, there must be an electric field acting on the charge. So the electric field is present, but again, it is not constant. It follows the 1 over r squared as well. So let's talk about the energy of the charge as it's moving towards and away. So as this charge moves towards big positive, it's feeling a force in the opposite direction. So it's feeling a repulsion. And if you want to think about the work done by the field, the work done by the electric field here is going to be negative. The charge is moving forward along its displacement, and the force is against it, so the field is doing negative work. And if you think about that, what that means for our rules of nature, the potential energy must be increasing. And conversely, the kinetic energy must be going down, which makes sense. As that positive approaches the other positive, eventually it's going to get to a point where it stops and say, I don't want to get any closer to that other positive. Once it reaches its highest point, at this location we've got maximum potential energy and 0 kinetic energy. The charge will stop and it'll have all the potential energy it can ever have. But objects don't like to have lots of potential energy. They like to decrease their potential energy. So once it's at its maximum point, this little positive charge is going to accelerate away from the other positive. So there's your displacement. And the force is going to be in the same direction now. So on the way out, the work done by the field is going to be positive. When the field does the work, the potential energy decreases and the kinetic energy of the charge is going to increase. It's just like throwing the ball up in the air in the gravitational field, except for an electric field, we've got a changing force and a changing field strength. So we have kind of a second rule of nature here that you can put up, that objects in gravity fields will always accelerate away from areas of high potential energy to areas of low potential energy. And the same thing is true for charges. Charges will always go from areas of high potential energy to areas of low potential energy. So if you look at the field lines for Earth, the field lines are pointing in. Well, it's the same thing as the field lines for a negative charge. So a positive charge would act just like a mass in a gravity field. There's high potential energy up here, and as we fall towards the negative charge, potential energy is going to decrease. So we're getting lower and lower energies. But there's one little trick with charges that's different than masses. That bottom charge there we have is negative. I could switch it and make it all positive, which means that the location of high potential energy and low potential energy can switch depending on the charge that's providing the field or the charge that's actually interacting in the field. I could put an electron in this field and watch the electron move differently than a proton. But that's a rule for another time. So looking at the scenario we just did, we have a positive charge being shot towards another positive charge, or we could switch that scenario up and take a positive charge and shoot it towards a negative charge. How would that be different? Well, I've got 4 graphs here. There's 2 graphs here that represent the potential energy of a charge getting close to another one. 2 of these graphs are energy graphs, and 2 of these graphs are force graphs. What I'd like you to do is figure out and vote which ones you think are actually the force graphs and which ones are the energy graphs. Write them in your notes and we'll debate them tomorrow. So the first scenario is the positive charge shot towards a large positive. I want you to tell me, is graph A the energy curve for that charge approaching another charge? Take 0, the origin, to be the large charge. And is B the force graph for a positive pushing away a positive? So you need to match up 2 of these letters with each of these choices. Positive shot towards positive and negative shot towards negative. Which one is the energy graph and which one is the force graph? So figure out which one is which, and we'll talk about these scenarios tomorrow.